Oh, am I recording? Yes, I am. All right. 7.4 is trig equations. So we're solving equations with sometimes simple, sometimes more complicated trig equations. So the first one is a relatively simple one, which we've definitely solved before. So what we're trying to do is find the angle where the sine of the angle equals 1/2. So being a visual person, I always, even if it's not on the paper, in my mind, draw a little unit circle. And I think, where is sine 1/2? So sine is 1/2 when the height is small like this. And it always happens twice in a period, which is from 0 to 2 pi. One period is from 0 to 2 pi. Right? Okay. So there are two angles that make that true. This one, which is pi over 6. And then the one over here, so that's 5 pi over 6. So two solutions. But what if we find all solutions in the universe going forever in both directions along the theta axis? Or around and around and around the unit circle, both forward and backward. So let's look at one of the answers. So this is a separate set of directions. So if we start with pi over 6 and we go all the way around the circle again, we'll have the same terminal side, so that will be another solution. So we can add 2 pi. I'm not going to write it down yet, and I'm leaving a space between the 2 and the pi on purpose here. So I can add 2 pi, but then I could add 2 pi times 2, right? I could go all the way around the unit circle another time. So I could add 2 pi times 3. I could also add 2 pi times -1, and I would go in the reverse, and that would give me another answer. This is theta. So if I say 2 times k pi, it does not matter where the k goes, but usually we have coefficients in front and then variables after, so this is kind of the standard order of those factors, where k is an integer. Integers include negatives. They're the counting numbers including negatives. That gives you all the solutions. Does that make sense? And then likewise for the other one. So if we start at 5 pi over 6 and we go all the way around the circle as many times as we want in any direction, that gives us another whole set of solutions. Now, I could not say it's pi over 6 plus pi, thinking that I'll go halfway and then halfway, because notice that would be different. If I went halfway around the circle, I would land over here, and sine is not 1/2 there, it's negative. Okay, great. So next, we're going to move on to an example where we're doing cosine, and this one's not a special angle, so that one was a special angle and this one isn't, so we're going to practice with that. So first we would type in cosine inverse of -0.65 into our calculator. Make sure you're in radian mode, because if it's not stated, we assume we're in radians. There's no clue here as to whether we're so that it's in radians. So if we type that into our calculator, it gives us 2.28. So that's an angle. It doesn't look like an angle because the pi is not explicitly stated in there, but that's an angle. So wherever that angle is, there's always another one, right? There's always two if we're considering a full period. So if I do a rough sketch of my unit circle, and remember that pi is over here, and pi is approximately 3.14, so pretty close to 3. 2.28 would be somewhere in quadrant 2. Right? So one of my answers is 2.28. And the other one, to find the other value where cosine is negative, that would be this angle over here. That one, where this reference angle is the same. So to find the other angle, I'm going to do pi minus 2.28, and that'll give me my reference angle. right? That would give me this. And then I take pi and add the reference angle. So pi plus the reference angle that I just calculated. And that would give me, did it earlier, I did it earlier and I didn't write it down. I did write it down. Oh, I did write it down. It works out to be 4.0. I didn't show the work here, but I did it earlier. So my two answers are the angle could be 4.0. That was rounded. It's just the next decimal is smaller than 5. And 2.28. Now, what if I want all solutions? So similarly to the previous example, if I start with one solution and I add 2 pi, that would bring me all the way around the circle again and get another one, and all the way around the circle again, and all the way. So we get 2.28 plus 2k pi, where k is all in integers. And we get another set for this one, 4.0 plus 2 pi. There's gotta be a way to pause. Okay. So this one's going to be different. We're going to start working on it before we figure out why it's different. So no clues as to what unit. So we're going to still stay in radian mode. And remember, the range of tangent is all real numbers, the output. So it's okay that I get a value bigger than 1 for tangent. So I am going to get an answer. So I type it into the calculator because that's not one of our special values. So tangent inverse of 2. And that gives me 1.11. So one of my solutions is 1.11. So usually I draw a unit circle, but I feel like with this one, it's more clear what's going on if I draw the tangent function on an xy plane. So remember, tangents look like those pinwheel shapes. So one of them's here. The asymptote is at pi over 2. And then we get another pinwheel shape over here. So this is at pi. And then the next asymptote is at 3 pi over 2. And so on, and it continues, right? So my first angle, 1.11, is in quadrant 1, right? So it's going to be somewhere over here. And I, no, just paint that. So it's somewhere over here. So if you look, where are some other solutions? I'm going to get another one where I land in the same y height. So this is my y of 2. I'm going to get another one here and another one here and another one here. So how far apart are these? Well, they repeat every horizontal distance of pi. So every distance of pi, we get another solution. So that's different than this. So how is this one different? First of all, the period is different. The period is pi. And secondly, whereas we had 2 solutions in one full period for both of the previous examples, for this example, we only have 1 solution in the period, because you can clearly see when we look at it this way that all the other y values over here are negative. So there's only going to be 1 solution in 1 period. So the all solutions, this was my 1 solution in the period, and my all solutions would be, I take my 1 solution and I can add all the multiples of pi, 1 pi, 2 pi, 3 pi, negative 1 pi, negative 2 pi, negative 3 pi, and so on. So again, k is an integer. Still doing okay? Okay, so now we have an equation that's more complicated. Those were all equations, but they were really simple. So now we have to solve this one. So pretty straightforward. So 2 cosine theta equals negative 1. Divide by 2 cosine theta equals negative 1/2. So now it looks like the ones that we've been doing. So we just have to think, what are my two angles? Because we know when it's sine or cosine, we're always going to get two solutions in one period. So where is cosine negative? I draw myself a little visual. So cosine is negative over here and over here. So I get cosine, oops, I drew the wrong way. Here and here, those are the ones that work to give me cosine negative 1/2. So this one is 2 pi over 3. And this angle is 4 pi over 3. And it says find all solutions. So for each of those, I add 2k pi, and that gives me the whole set of solutions. And I do have to keep saying k is an integer. Because if k was a half, for example, I would not land on another terminal side, coterminal side. Keep going. Here we go on this one. Still not too complicated, but I want you to see all the variations. So now I have tangent squared equals 3. Take the square root. Don't forget, get plus or minus. So now I have tangent of theta equals plus or minus square root of 3. That's really important. If you forget that it's plus or minus, you're going to miss a whole set of solutions. So those are special output values for tangent. So the two places where tangent equals positive square root of 3 and negative square root of 3. So the positive is at pi over 3, and the negative is at 2 pi over 3. And then if I want all solutions, this is tangent, so I'm going to add multiples of pi, not multiples of 2 pi. So plus k pi, plus k pi. K is an integer.